The James Webb Space Telescope has safely reached its destination, the second Lagrange point, or L2. In the spring of 2022, it only needs to align its 18 mirrors. Teams of scientists already have the forthcoming years planned out. Webb will check how black holes absorb matter, and it'll peek through previously impregnable walls of cosmic dust and see how stars are born. But all of this is just going to be daily routine. Webb is also preparing for much bolder tasks to fulfill. In this video, you'll find out: how can the new telescope help us find dark matter? Will we see other universes reflected in Webb's gold-plated mirrors? And what's the real reason behind launching the James Webb Super Telescope into space? Can the JWST and its observations help us determine the exact expansion rate of the universe? The Big Bang Theory states that the universe is constantly expanding. Stars and galaxies that aren't held in place by gravitational attraction move farther from each other with every second. If we figure out the precise velocity of their movement, we'll be able to see what will happen to our Milky Way in the future, and vice versa, what happened to it in the past. However, attempts to define this crucial cosmological parameter have produced probably the biggest contradiction in modern science. The expansion rate of the universe is called the Hubble constant and is measured in kilometers per second per megaparsec. Astrophysicists have developed two calculation methods, but here's the problem. The results achieved by different scientific teams don't match up. I mean, at all. The first team determined the expansion rate based on the cosmic microwave background. This is the relic radiation left over from the days when our universe was a young beauty, about 380,000 years of age. If we compare it with a 20-year-old girl, its microwave background would be a photo of her as an infant born 5 hours ago. Using this microwave background method, the first team finally discovered that the universe expands at 67 kilometers per second per megaparsec. As for the second team, they watch how the luminosity of well-known stars located several million light-years away from us changes over time. This time, we're looking at yesterday's photo of the young universe. But wait a minute, this should be the same person, but it seems that it's not. Besides, the expansion rate of the universe determined with the help of stars comes to 74 kilometers per second per megaparsec. So there's a 10% difference in the results, and it's hardly explicable. Can the JWST check which of the options is correct? Well, yes and no. The first team's cosmic microwave background is 100 times longer than the emissions the telescope can capture. It's like trying to look at a python under a microscope instead of an ant. In turn, Webb's mirror is 6.5 meters in diameter and can collect enough light to detect the slightest change in the luminosity of relatively nearby stars. This means that the second team will finally be able to give us super accurate information on how fast these objects are moving apart. But what makes the universe expand in the first place? We'll never know the whole truth unless we find an essential missing piece of this puzzle, an invisible and all-pervasive substance that fills the entire volume of space. How will the James Webb Telescope's observations help us understand the phenomenon of dark matter? Astrophysicists have noticed that some galaxies move like they have much larger masses than we can see. This missing invisible mass is called dark matter. According to contemporary studies, there's 6 times more of it in outer space than all the stars, planets, and cosmic dust put together. The well-researched gravitational lensing effect will come in handy to help JWST find dark matter. This effect happens when a gravitational field of a massive body bends the light traveling towards it. Compared to the Hubble telescope, Webb will be able to spot much more distant gravitational lenses. That'll allow scientists to discover new clumps of dark matter and determine their masses. This will bring us closer to understanding what this substance really is and what it's made of. This idea is the cause for ongoing disputes. Yet some astronomers assume that dark matter is something that all space lovers know very well. That's right, black holes. Although not the ones you're used to. Prehistoric black holes could have appeared less than a second after the Big Bang from high-density areas in space. These immense monsters could still be out there lurking unnoticed. That's like hidden pockets that you can see only if you turn your garment inside out. And since a hole of this sort isn't formed due to the explosion of a star, it could have a mass equal to something as small as a speck of dust to something as massive as an entire galaxy. It was in the early 1970s that Stephen Hawking suggested that dark matter could be composed of these primordial black holes. Although even the Webb, however sharp-eyed it is, may have problems finding a primordial black hole on its own. It'll need a mighty sidekick to cope with this mission, like Doctor Strange in the latest Spider-Man movie. In 2034, space agencies will launch the LISA Gravitational Wave Observatory. It'll detect the slightest fluctuations that massive bodies can cause while moving. Then LISA will hand its notes over to the James Webb Telescope, and our superhero will investigate the area. Going back to Stephen Hawking, he's also known for a theory even more extravagant than the one about prehistoric black holes. And if our telescopes confirm it, Copernicus' revelation that Earth's not the center of the universe will sound like a lame joke from a third-rate comedian. Will the data collected by the JWST confirm the multiverse theory? In 2018, the attention of the scientific world was focused on Stephen Hawking's last paper entitled A Smooth Exit from Eternal Inflation, co-authored with Thomas Hertog. Of course, here we're not talking about the kind of inflation that makes a gallon of gas more expensive. This is cosmic inflation of the early universe. A regular explosion spreads evenly in all directions, but our universe suddenly started to expand exponentially soon after the Big Bang. In a matter of split seconds, it grew from the size of an atom to the infinite space where we send our costly telescopes like James Webb. And whatever we do, we'll never see where it ends. The problem with the eternal inflation theory is that, according to it, similar abrupt expansions keep happening in different regions of the universe. As a result, there's an endless number of new universes. Oops. Hawking and Hertog trashed this theory in their article proving that cosmic inflation can't last forever. Just like economic inflation can't make a gallon of gas cost who knows how many dollars. Consequently, it turns out that if other universes really do exist, there aren't so many of them, and they don't offer a wide range of conditions. Roughly speaking, you could have a different profession in a parallel world, but your national identity won't change. What's most unbelievable is that scientists have found a way to check Hawking's multiverse theory. To do so, we need to equip a spaceship with a special detector. It could find evidence of other universes in the microwave background left over after the Big Bang. But remember what I told you, this wavelength is 100 times longer than what the Webb can detect, so our dear friend is helpless here. But don't get discouraged, though. The most fantastic worlds lie not in some mythical parallel universes. They're right here in our galaxy. Will the James Webb find signs of life on exoplanets? As of 2022, there are already more than 5,000 discovered exoplanets and 2,000 more possible candidates. But who cares if all of them are lifeless? That's why scientists keep passionately searching for habitable worlds. Here's the clue. If a planet has any live organisms on its surface, they'll definitely leave behind typical atmospheric biomarkers. Above all, these are molecules of water, ammonia, and methane. But the main surefire sign of life as we know it would be the presence of chlorophyll. This pigment gives plants their green color, which is vital for photosynthesis. Chlorophyll absorbs visible light, and it's seen perfectly in infrared. If Webb captures an anomaly like this on one of the exoplanets, this will mean that plants are growing there and getting energy through photosynthesis. If there's an abundance of phosphine gas molecules, everything will point to bacteria able to survive without oxygen. Quite recently, astronomers detected traces of phosphine in the clouds of Venus, but we'll need additional research to better understand its origin. Anyway, Even the most powerful ground-based telescopes can't detect any of these biomarkers on other planets. They're simply blocked by the Earth's atmosphere. There's also no chance to find life using the Hubble, as it works in the infrared range where biomarkers go unnoticed. Webb, on the other hand, can observe a 10 times wider portion of the infrared spectrum, and if there are any biomarkers on any exoplanets, it'll spot them. And yet, astronomers' #1 dream is to discover a highly developed civilization with its own unique markers. If aliens are searching for people, they could find us by observing the very high concentrations of carbon dioxide and monoxide, ozone, and lead in our planet's atmosphere. It's thought that the Milky Way contains around 1 billion terrestrial-like planets, so the chance of finding at least a primitive life form is higher than ever. And that's going to be the James Webb's most valuable gift to humankind. I wonder what astrophysicists are going to do after they solve all the mysteries of outer space. Perhaps they'll take a break from the painstaking exploration of the universe. They'll turn on some relaxing music, make the Webb radiate some gentle infrared in the background, and lazily watch how some intergalactic love affairs play out. What? That's important for cosmology too.
Subscribe now and press the bell icon. Never miss an update.